我想现在回。
害怕是因为我觉得你要先定义出来，然后先定义那个 line。
上面那个 proof 有用到什么？然后就是前面的 proof，如果
前面没有
用到就需要吧，
前面没有
如果没有用到就不需要吧。
啊，没有，就是那个 prove 它是 projective space 的时候，projective plane 的时候是需要的，
哦，这样就需要。
所以我把顺序换了一下。
那个 proof 其实我没有写嘛，可是 linearly independent 应该不难看得出吧？
是你这里的 linearly independent 是什么意
就是
思
正常的 linearly independent，
？OK，
应该看不出。
你怎么能说两个点是 linearly independent？
因为那个两个点其实是个 vector 来的。
当然，我大概能 get 到你在说什么。
Yeah，嗯，没有特别介绍什么叫 linearly independent，不懂。
觉得没什么，然后就差两个题，
嗯
题目前也差两个题，然后再加那个六次的视频，我还会讨论。
，OK。哎，我们上次这边有 probability 在上课吗？哦，是有。
B 吧？哎，不懂啊，但是有的
哦，是吗？有遇到。
那好像那所有人是我去，
第一下课他会准时下课。
下一个比较基本。
我还好。我们要不要猜一下，下次他会不会准时下课？我赌他会。是他会，真的是他会，但是他真的是啊。所以你看，所以
你讲是后就在这里，
对对对对对对，
那不是
是啊。我也没有，我上个礼拜没有注意到有一堂课在那边。
是我慢来。对，那时候
我慢来，
但是也是死定。
那我慢来哦。
这样，你想要做
啊，没有，我是猜，他可能下个礼拜会准时下课。看见。
要不要把你那个题刷到出来？
哪个？
那个是什么第二个，给他第二个。
哪个？就下面那个。
就是
这个
不是这两个，这是你
这个好像不太，这个不太完整。其实这
对，
个是我之前画的，这个是我今天早上画的。
你觉得你这个画的看得清楚吗？
我觉得等下我解释看看，再说。
我觉得看不清楚，尤其是你跟我来的了。
对，我再看看，要解释。
如果他没有不是镜子的图之前，我就插一个手或者出来。
不介意啊，不介意啊，这个我还好。
那你会介意如果我们实在来不及就直接换的时候？
也不介意啊。
或者不介意啊？我插四个电在那边，
擦你擦，
可以啊，
你擦。
电什么都不介意。
What？
等一下我1个小时休息时间，还有
OK，
一点点电。 还是你拿一个椅子放那边擦，等下会跌倒的。
等一下，等一个小时。
这边也有，这边有一个椅子啊，应该有人擦过。不然像你家浪费了写这样多东西，还是解释一下。Hello, testing. Okay, I think we will clean up geometry a bit before we jump into commutative algebra. Okay, first thing first is there's an equivalent formulation of P3 and P4 just by one axiom here. So this axiom is there's this 4 points in which none of the three are collinear. Okay, so this one is equivalent to P. And you can show it. And I attached this working from one of your classmates, Hao Tian. So I was thinking of giving this type of assignment question, but since someone has done it, I just share it to you. Then we will have others question on. We can do more questions in that case. Actually, there are a lot of questions that I want to put in, but I was still deciding what to put. Okay, yeah. So you can actually show that this point here is equivalent to P3 and P4. Actually, this similar statements appear in projective tree space, right? In the axiom of projective tree space. Okay, this type of statement. I need to be very clear. So let's see. Do we have similar statement here? It's the projective tree space. Yeah. So you see in S5 here, there are 4 non-coplanar points. Okay. Yeah. So very similar. So these axioms are replaceable as long as they are equivalent. Okay. It's not that they, they can be replaceable. Okay. As long as they are equivalent. And yesterday, for the proof of completion of the affine plane is a projective plane when we're proving P4, right? I use the existence of 3 collinear point here. Actually, my line is working in A. Okay, so I just need A3 is enough. Okay, but obviously you can use P3 to try and prove P4. So meaning you directly start with a line in P4. Okay, and then use existence of 3 collinear line in P3. And in that case, maybe you need to consider a point of infinity. Okay, so you can try and work that way out. Okay, so that's an exercise for you. And last time we jumped pretty fast on the Sachs theorem. Okay, the Sachs theorem says what? If two triangles are perspective from a point, okay, you look from a point and then you can see that there's a line joining. There are 3 lines joining the vertices of triangles. Okay, then the 2 triangles are perspectives from a line. Okay, meaning if you elongate all the edges, again, then you look at the intersection of corresponding edges, they should intersect. Again, moreover, the 3 intersection lie on the same line. Okay, actually, it is not too hard to prove. Okay, if you remember this picture here. So how do you make sure that these 3 intersection point here lie on the line? Okay, if you can imagine this triangle here could span a plane. Okay, could span a plane. And then those elongation of the edges obviously live on the same plane. So in this case here, you have 2 planes. Okay, so 2 planes will intersect at a line. Okay, 2 planes intersect at a line. Okay, can you imagine what I say? Okay, so this triangle here should live on the plane, right? And then the other triangle here should live on the other plane. So this line actually is the intersection of 2 planes. Okay, so this reduced to a question proving that two distinct planes will have a unique intersection, which is a line. Okay, so you need to use a S1 to X6 to prove that this work. Okay, actually I prove it for you. So it's a very routine exercise, okay, to prove that in projective tree space, two distinct planes meet in exactly one line. Actually, the idea here is really similar to two distinct lines meeting at a unique point, okay, in affine plane. Okay, similar idea. Okay, very similar idea here. I'll put the rest into your tutorial question to prove this using the axiom, using the axiom of projective tree space. But there's another case. There's another case. What if this? What if these two plane? Sorry. What if these two plane here coincide? Okay, meaning they sit on a flat plane. The two triangles sit on a flat plane, same plane. Okay. Then where's the intersection? You cannot use this method. You cannot use this argument here. But you can turn it into two triangles that are living on a different plane. Okay, you can turn it to that. So how do we do that? Okay, so how do we do it? So let's do it. Let me show you some magic here. So let's just start randomly. Well, right. So all similarly is the same. Let's start from a triangle that is perspective from a point, okay, but living on the same plane. Okay. Like this. Okay, let's draw some trick here. Okay, let's do one on this side. Yeah, the other one on this side. Okay, and let's draw it like this. The other one. Yeah. Okay, so let's call the first one A. Sorry, use this one. A, let's keep the same one. So A, B, C. So clockwise. A prime, B prime, C prime here. Okay, they live on the same plane. How to create two triangle in a different plane? Okay, so what do we do here? Well, we can choose four non-coplanar point, right? Right, so we can, out of this plane, we can pick another point. Okay, let's call it X. Let's call it X. Okay, so what we're gonna do is we form line between X and each vertex here. Okay, we form line with each vertex here. Okay, let's wait. Okay, let's do it. Finish this first. Let's zoom in a bit. Okay, and the center of perspective here, we call it O. Right, and then what we do next is between X and B, we choose one point. We choose one point. Let's call it D. Let's call it D. And then from this center of perspective, we draw a line from O to D. This line is to guarantee to pass through XB also, the line joining XB, where we will call this point D prime. Okay? Does it make sense? What I'm doing? Okay. And now I'm gonna link the two triangle up. Okay, I'm gonna link the two triangle up. So what I would do is I'll join A to D, join C to D. Okay, and then join C prime to D prime, and then join A prime to D prime. Okay, does that make sense?
So how do you imagine this? It's like you pick the vertex B and D prime, and then you put it up. Imagine or not?
Okay, so it's like you take this line here and then you lift it up. Okay, lift it up. Okay. All right. So in this case here, then these two are the perfectly good cases from previous consideration, right? Okay, so it would have a perspective from a line property. Okay, we'll have a perspective from a line property. So where's that line? Can we draw it? So let's see how we draw this. Bit challenging, but let's draw it. So let's extend this, and then we will extend this. Wait. Like that. So this one is AC and AC, A prime, C prime. This is the only thing, the only line that we didn't lift it up. Then how about the rest? AD, AD like this. Okay. AD prime like that. Okay, so this one AD and D prime. And we still have CD and C prime, D prime. So let's draw it. That. Then this guy here, long enough. That's it. Okay, not long enough. So let's try again. Okay, so let's get rid of this guy. Get rid of this also. Okay, and we are meant to join these 3 points here by previous case. I hope I can successfully join them. Okay, about the same, okay? I think okay. Okay, right? Okay, a bit off, but okay. Because I think because of the thickness of this line, a bit hard to control the exact. Okay, can you see that the join it? Okay, but then we need to argue that this line here, once you project it back to the same plane, it still remain a line. Okay, but projection should preserve what? Intersection. Okay, projection should preserve intersection between lines. Okay, so all these are intersection between lines. Correct or not? Okay, and projection also send line to line. Does that make sense? Okay, so we can project this the two triangle back to the two triangle on the plane, and then we project that line of intersection back to a line of intersection. Okay, but a bit non-trivial if you try and draw out the perspective from a line in the plane. A bit non-trivial here. Okay, let's call them some name here. Okay, between AC and C prime, Q prime, we call it Q. We call it Q here. And then between A D and A prime D prime, we call it, what do we call it? We call it P. Okay, and then P prime, and then the last one we call it R prime. Okay, let's look at the bottom intersection here. Let's look at the bottom intersection here. So if we elongate BC and BC prime, what happened here? If we elongate BC and then B prime, C prime here, we got this point here. Okay, and then if we elongate AB, get AB, And then A prime, B prime is here. Okay. Hopefully we got another line joining these 3 points. So let's hope that we are successful. But oh, okay. About there. Okay. Okay, cool.
So, but what can you see here? Seems like the order of this P prime R prime Q is different. You see, Q is in between what we started with, what we call as P and R. Okay, but in this projected out lines, right, you have a Q at the bottom. Okay, so there's some subtlety happening here.
So let's label them. So what do we call the point that intersect between AB and A prime B prime here? So this will correspond to AD and AD prime, which is P prime. So this point is P. Okay, so this is originally P. And then the last one is. Okay. So yeah. Okay, so you can see that Q goes to P, but the R here, R prime here suddenly move to the others. Remember, this is not in R5, this is in projective space. Okay, so a bit counterintuitive here. Okay, a bit counterintuitive here. So let me draw a bit longer, see what's happening. A bit counterintuitive.
Okay, can you imagine Can you imagine how you project down this building? When you project it down, what happened? And that R prime intersection, right, become very far away. You open at the other side, but need to close on the other side. But still, the intersection between line is preserved under projection. So all these collinear property are about intersection between lines. Okay, so it preserved by this projection. So collinear lines get sent to collinear. Okay. Any question? Can you imagine? Okay. Yeah. Okay. So, and then the one very interesting corollary is if you study this, okay, before that, this the Sachs theorems, right, who work for any plane inside projective tree space. Okay, because the second case is just talking about plane. Okay, so it will works in plane in projective tree space. And then you should prove that any plane in the projective tree space actually satisfy P1 to P4. Okay, so yesterday I said that if you satisfy P1 to P4, it's not guaranteed that you have P5, have the Sachs theorem. But if you are a plane in a projective tree space, you build with the Sachs theorem. Okay, so if your plane come from projective tree space, you will have the Sachs theorem. Okay, so meaning what? The plane, they call it the plane that doesn't satisfy the Sachs theorems, right, cannot come from projective tree space. Okay, just usual plane that satisfy P1 to P4. Okay, don't go and find the counter example from projective tree space. You cannot find it because I proved it to you already. Okay, and the converse actually hold in a P2. Okay, the converse actually hold in P2. That is, if the triangles are perspective from the line, you can prove that it is perspective from a point. Okay, and this will use the duality inside P2. Okay, maybe you listen that. Maybe you hear the word duality is a very big word. Actually, it's not. Okay, so the duality here just says that there's a bijection, okay, between points and line. That's all. Okay, anything that's true about point will be true for line. There's a bijection between these 2 points. Okay, the duality inside E2. And then this is the another reason why I want to bring out the structure here. I want you to see some duality inside algebraic geometry. Okay, inside algebraic geometry, there's a lot of duality concept. Okay. This is one of them. Okay, there's some statement about points, some statement about line, they can exchange. Okay. Does it make sense? Any question? I think good timing. Any question? Okay, for those who came late, I will put out this equivalent axiom by work out by how can here? Not work out, just prove by how can. Okay, I will put it on. Basically, you replace the P3 and P4 by this single axiom here. There's this 4 point in which none of the 3 point are collinear. And then the other thing is yesterday, the proof on P4, right? I actually didn't really need P3. It's an accident. I read it wrong because I actually start with a line in A, so I should use A3 only. Okay, but if you want to prove P4 by P3, you are welcome to do it. Okay, as an exercise. Okay, that's all. Anything you want to ask me before we continue to the next section? Anything you want to ask? Anything? Okay. Okay. Uh, in that case, I want to remind you, please meet this week before meeting me next week, and then tell me the time you can meet with me. If we don't meet during office hour, then we might need to find a place. So you need to tell me earlier. Okay? Yeah. All the group member have to meet with me. And please decide a leader among you. Okay, and then tell me as soon as possible. Okay. Let's go to algebra part. So previously we do purely geometry. Now we will do purely algebra. Okay, we do purely algebra. So let's do commutative algebra. So commutative algebra will assume a little knowledge from group and ring theory. Okay. If you forgot, maybe we can remind you. All right. So let's start from the first important definition. A ring, okay, a ring is Noetherian. Okay, Noetherian. So this name is in honor of Emmy Noether. Noetherian, if it satisfies the ascending chain condition. So we will abbreviate as ACC. Okay, one more C than echo. Okay, ACC. Okay, meaning uh, every ascending chain. Okay, so what does it mean by ascending chain here? So it is just A1 contained in A2 and then so on. Okay. Could be non-stop, but if it is ACC, we want this is a chain of an ideal terminate. Okay, it must stop. Okay, so how it stops? It stop doesn't mean that it really stop, nothing behind it, but it stays stationary. Okay, so the chain can stay or eventually stationary. Stationary. So what does it mean by stationary here? Meaning that this n in n such that in equals to in plus 1, in plus 2, and then so on. Okay? Make sense? All right. So let's give some Noetherian ring here. So for example, Z is Noetherian. Okay, Z is Noetherian. Z is a principal ideal domain. correct? Or not? Z is the principal ideal domain. Later we will touch about principal ideal domain again. Okay, Z is Noetherian. So you should show that every chain stop here. And then Kx is also Noetherian if K is a field. In that case, let's talk about field is Noetherian first. The field K is Noetherian. Okay. So in fact, any PID, yeah, principal ideal domain is Noetherian. Actually, I think I need to pull out the PID domain definition first because later we will touch on it as well. Let me see. Is it necessary to move things up first? Maybe not. I will just leave it here for now. Maybe in the action notes, I will do some adjustment. Okay. And one last thing is before we jump, let's give a non-example. Okay, x1, x2, and so on. Okay, you adjoin infinitely many variable here. It's not Noetherian. Okay, seeing this is not Noetherian, right? Not Noetherian means what? There exists a ascending chain that doesn't terminate. Can you give me an ascending chain that doesn't terminate? Any idea? Ascending chain that doesn't terminate. You can have ideal getting bigger and bigger and bigger and bigger and bigger and bigger. Yeah, X ideal generated by S1, ideal generated by S1, S2, ideal generated by S1, S2, S3, and then you can keep at your generator, at your variable as your generator. Never stop, right? Okay. Okay, so this ascending change doesn't terminate. Okay. Okay. I will leave the any PID is a Noetherian to later. I think it's better. I mean, I will do it later actually. Okay, so this one I leave for later. Okay. Next. So let's do some proposition here. We will have a few equivalence way to see a ring is Noetherian. Okay, so these way are very convenient, depend on what ring we are looking at. Okay, so obviously the first statement is ACC. Second statement is a maximal condition. So what's this maximal condition here? So every non-empty set T. So what is inside this set here? These are all ideal. Okay, ideal of R has a maximum element. Okay, so I think most of you will know that this is a Zone's lemma actually. Okay. And how about third property here? Every ideal is finitely generated. Okay. So this one is one to prevent what we had just now, the counter example we had just now. If every idea is finitely generated, you should hope that you have an ascending chain condition. Okay. So that is for every ideal I in R, and there's this finitely many generator in I such that I is equals to the ideal generator by F1 up to. Okay. How about I give you 2 minutes to think about it?
2 minutes to think about it. You can discuss with your friend before I tell you the answer. Okay, so when we talk about maximal elements here, right, we need to know what's the partial ordering. So what's the partial ordering in ideal? What's the partial ordering here? Sorry, subset inclusion. Okay, subset inclusion is the subset inclusion. So meaning that if they are subset of each other, you can include the ideal into it. Okay. So what's our strategy here? So basically, I think you can do in different ways, but we're gonna prove. We want to show one if and only if two, and one if and only if three. So I would move the tree here. Okay, so this is what we're gonna do. All right, let's see. Maybe not too long. I think we can do it. So let's do one way first. Let's do 1 to 2. Okay, so let's do 1 to 2. So 1 to 2, how to show? Suppose 2 is false. Any idea? If 2 is false, what happened? There's one empty set of ideal does not has a maximal element. Then that is the chain you need, right? To contradict the terminating ascending chain. Correct or not? It doesn't have maximal, right? So you can keep go on. Okay. So we can construct inductively a non-terminating increasing terminating ascending chain where's T? Chain using the ideal in okay, saying there's no maximal guy. You just keep going. Okay. How about 2 implies 1? So if you know that every non-empty set of ideal has a maximal element, how do you prove that every ascending chain terminates? So you take the ascending chain, right? Okay. And then what do you do next? The chain,
you can just combine them into a set, right? But what does the statement 2 tells you? Any non-empty set of ideals should have a maximum element. So where does the chain terminate? Terminate at the maximum element. Okay. Okay. So every ascending chain of ideal will terminate at the maximal guy. The maximal element. Okay, good. Let's do 1 to 3 now. Okay, so you know something about ascending chain, but now you want to prove that every ideal is finitely generated. Okay, so how do you construct ascending chain from a given ideal? Let's start with an ideal. Increase what? What do you mean? Ah, ideal of generator? What do you mean? 喂，不要这样讲话诶，讲一些正常的话诶。Think properly. What do you do next? You want to take an element not in I and then add it in? Then what? Sure. Obviously, you get something bigger. Then what do you do next? Okay, let's see what you're gonna crazy idea you have. So you got something like this, is it? Okay, so let's take U in R, not in I, and then you have I inside I in U like that, and then again like that, and then keep going. No, you can have idea, but you should think a bit longer, right? What? So you just want to take something and then combine them. So this guy have a maximum guy, obviously. Okay, good. Then how can you talk about I? What's okay, talk about I. So just I will live in some ideal generated by I with finitely many things. That's all. But you haven't tell me something about I itself, whether it can be finitely generated or not. So you want to use contrapositive. So let's see. If this ideal is not finitely generated, then there's a chain. Sorry. So if it is not finitely generated, then there exists an ascending chain such that it doesn't terminate. Yeah, I think it works. It works. Yeah. So this basically this is like how we prove K adjoint X1, X2, X3 are not Noetherian. And instead of using variable, you use the generators. Yeah, it works. Okay, it works. But I think I got a direct proof. Maybe I just leave it in the notes. Hmm? You want to discuss direct proof? Not necessary, I think. Just leave it for you. Huh? Or you want to discuss? You want to discuss? Huh? You want to hear? 随便. How about others? Discuss. Okay. Let's look at how about direct proof? So if you use the contrapositive, it's a similar proof that K adjoint infinitely many variables is not Noetherian. So if it's direct proof, I found this proof here. So let's consider the set. The set of all finitely generated ideal. Sigma, yeah, sigma ideal. J contain in I. Okay. So this sigma would be for the J in I such that J is finitely generated. Okay. Well, if we're gonna use one here, hey, what am I doing here? I think I'm not using one. I'm using two. Okay, I think I confused already. Wait, let me see. What is my logic here? I think I confused because okay, the story is like this. I look at a lot of implication and then I pick something that I like and then I put them together. But I think because in different book they have different labeling. Yeah, different labeling. So I think I confused here. So I think, okay, so let's keep the one that you say just now. No wonder becomes so easy. If we do 1, 2, 3, just use contrapositive. But in this case here, I think this is doing 2 to 3. Yeah, this is 2 to 3. Okay, I'm doing 2 to 3 here. Okay, let's see how to do 2 to 3. Ah, 1 to 2, what do you mean? 1 to 2, 2 to 3, 3. Oh yeah, sure. I mean, this doesn't matter, but what's matter is this proof is going to use 2 to 3. Going to prove 2 to 3. Yeah. Yeah. We will definitely have the order, right? But I mean, have the logic, right? But I just confused with the numbering here. Okay, but I think no wonder 1 to 3 becomes so easy because it's just contrapositive. And then let's do 2 to 3 here. Okay. What I'm gonna do here is 2 to 3. So meaning I want to use the maximality to prove that every ideal is finitely generated. Okay. So to use that, we need to show that this set is not empty. Okay. So why is this set is not empty? I is in there. I don't know I is finally generated or not. Okay, but zero. Zero is in there. Okay, zero is in there. Okay, zero is very good, a good friend. So by assumption, sigma has a maximal element. Let's call it J naught. Okay, call it J naught here. If J naught equals to I, then we are done. If J naught equals to I, we are done. Okay, so suppose J naught is not I. Let's suppose J naught is not I. So what do we do here? For here, we will use the technique that Adrian play around just now. So if you take an S, okay, that's coming from I, but not in J naught, okay, and then look at the ideal generated by it. Obviously what? Obviously, this is finitely generated. Correct or not? Because J naught already finitely generated, right? I just add one more in. Still finitely generated. Okay, one more generators. And this guy will strictly contain J naught. 3 contain J naught. Something wrong here. J naught is a maximal guy. Okay, so we have a contradiction. What's the contradiction here? Contradicting the maximality of contradicting the maximality of J naught. Okay, maximality of J naught. So I has to be equals to J naught. Okay. Okay. Okay, I only prepare 3 to 1. Okay, let's do 3 to 1. So 3 to 1 says what? We need to prove that every ascending chain terminates. So let's take an ascending chain. Okay. So in your mind, right, if it terminates right in an ascending order, right, meaning what? This ideal should be somewhat big. Okay, somewhat big. But you know that every ideal is finally generated. Okay. So what can you do here? Where can you apply the assumption that every ideal is finally generated? Okay, you could like look at all the II or IJ better. IJ are finally generated, sure. Okay, but you need to tell me where it terminates. Okay, so well, just now I show you right. Still, if you have every ideal to be finally generated, you could have a non-terminating ascending chain, right? In decay, adjoint, infinitely many generated. Everything is finally generated, but it still doesn't terminate. But once you add in the extra condition that every ideal is finally generated, then this change should terminate. Okay, so how? Where's the big boss here? How to find a big boss? Huh? Sorry? What? Ziqian, what do you say? The limit of IJ. So what's the proper limit here to look at? Yes, it's a union. Well, in the category language, it's actually a limit, yes. But look at the union here. Direct limit, huh? Okay. Yeah, it's a kind of limit. No, analysis limit is the algebra limit here. Okay, so we look at the union of everything. Is this an ideal or not? We proved right. We've proven before, right? Union of ideal is still an ideal. Okay, so this is an ideal. Set this, which is an ideal. Meaning what? By 3, we know that this ideal is finitely generated. Okay, so this giant here is finitely generated. Okay, so now how do you argue that this is the terminating guy? So which end it should terminate? Which end? How to find the end it terminates? So you have I1, I2, I3, and so on. So this Fi live in some of the IAJ or not? Hmm? Huh? Why? Because this I is the union of all IJ. I am here. Okay, so it should come from somewhere. Correct? So it should come from somewhere. So notice that this Fi here live in some, let's call it Mi. Okay? Depend on Fi, okay, where it live. And it doesn't necessarily that F1 must live in I1. Doesn't necessarily. Because we could have labeling also. But depends on. Then what can we do here is a very standard trick, standard trick. So we pick n to be the maximum of these mi. Okay, and then this will give that I equals to in, and the chain will stop at in. Okay, the maximum of mi where these mi live. Okay, in. Does it make sense? Okay. Any question? Any question before we take a break? Yeah, break on time 50. Any question? Okay, if no question, let's break until 5 o'clock.我不对劲，我中午不对劲。
准时下课了，变得很好说话，
对啊，
不觉得吗？
我觉得，但是我刚才遇到张丽萍老师，
我刚刚进来的时候也遇到了，怎么了？
没有，就是刚是你吧？
你 J 在拍里面
嗯
发生的，
你讲什么？
你 J
不在爱里面，
在爱里面会不会发生什么？
在爱里面会发生什么？
对，
杰诺如果在爱里面会发生什么？
J 是爱里面的新闻，
你讲 JI content 在爱里面
J
杰诺 content 在爱里面，没有什么啊，有什么？没有什么啊，也是这个情况的。不是，等一下你讲它 properly contain，
对，
但我也可以做这件事情啊，没问题啊。还是有东西我可以不在这，然后没有办法找。
哦，你讲 J
嗯嗯，
你的那个二跟左昂斯莱玛有什么区别？
啊
这个二和左昂斯莱玛有什么区别？
这个那个 maximum，
没有它的 element，
对啊，
那也就是说，如果它不是 Noetherian，左昂斯莱玛不成立。
可能还有其他地方
可以了，有什么问题？不成立。
左昂斯莱玛不是对任意 partially ordered set 成立？
等一下，你讲什么意思？不成立就不成立了。
可是左昂斯莱玛不是对于任意 partially ordered 的 set 都成立的？怎么会在这个地方突然不成立呢？
想一下你讲什么东西？
刚才你讲吗？
我说左昂斯莱玛对任何的 partially ordered set 成立，为什么在这个地方突然它的这个 set 不成立了？所以它不 Noetherian。
我相信有没有？
是哦，
想想看有没有讲错东西。钱
对啊，发生有就代表不某一天的来你的学历 order，对呀、你就写不出那个 chain 啊，那你怎么会有 maximum idea？
是 partially ordered 的。
完全
它这里 order 的只要求
没有什么 ring 里面的 idea 几不同的，那多难呢？是都不可以。
你的那个 subset 就是一个，
对啊，我想这有没有？有没有爬山有或者是不懂？没丢。再两。Incorrect。
是难怪你没有看到，因为我不照给你看。应该1到2，如果要照这个 maximum ID 的话，应该是要那个 Excel trace，但是我不是这样子证。
如果
感觉是，
如果
是这样子写的，
所以如果它不能为
这样子
T 人，会是怎么样的结果？
啊？
那如果它不能为 T 人会有什么结果？
什么意思啊？
如果它一个 set 不能为 T 人，那它的
他就布这些，布这个，布这个。
对啊，那2不是就没有一个 maximum？
有一个 non-empty set 没有。
有一个non-empty set，那对于这个 non-empty set 的 zone 3号不就不成立了吗？那对于
这个合理啊。
对啊，问题是 zone 3号对于每个 partial 要的 set 都成立。
那要是爬山或者
那这个 partial zone lemma 有要求不禁止吗？zone lemma 有要求不能静止，不能停止。
这样。
Zone lemma 没有要求不能停止。没有啊，没有什么要求。
可是这个爬山或者在它无静止的话，你也没有问题啊。哦，确实没问题啊。
Noetherian imply
但是可能
no extension。
every non-empty set，every non-empty set，every non-empty set 有包括整个 set 吗？
啊？
every non-empty set 有包括整个 set 吗？
啊
？every non-empty set 有包括整个 set 吗？
有啊，整个 set 肯定是 non-empty 的。
那一个 set 是无定值的话，你怎么说它有什么 maximum？
对啊，所以昨天 lemma 的那句话到底是什么意思？
启发
你说这个？
对，下面那个。
I mean 4和3是一样吧？
我现在还是没有办法理解4的东西。
写错，我觉得没有写错。
Any partially ordered set maximum。P 站
What are you talking about？
上 P 站学数学。
少写东西。
分啊，学过吗？很少还是真的爱教数学。是呀。可是他是华语，我听不懂。
你没有少写东西啊？写错了。
我屌
哪里？
这个还是 there is a maximum， 全部是 maximum。
喂。
OK， 我去再改一下看一下。我是从一个地方查。哎，如果东西就是这样，没有仔细讨论，一定是错的。
拜拜。
OK，不懂我要翻一下。
我怎么看怎么不会做？
那逻辑
我看它也太强了，我感觉
是有点强啊。
一直写太强了，因为前面本来要有一个东西，结果到了后面这个东西被你丢掉了。很强哎。
A partially ordered set in which any chain has 什么
这个是错啊，这个应该不是 element 来。
maximum？
如果这是 element 哦，你看这个跟这个的差别是这句，你不用再 check 这个了，这个
太难了。这边不是
哦。
什么？
啊，没有，你这边上面
这个对，这个就不用管了哦，你都不用 check 有没有 upper bound。
对啊对啊
对啊，因为
好像不是，好像不是。
对啊，你不觉得这个4很奇怪吗？他直接把一个题给删掉了。
我觉得如果这样强我也合理，我接受，但是他不是应该。so high. Okay, okay. Okay, let's start. Okay, let's start. Okay, so for this two proposition, I won't prove. I'll give you the proof in the notes. You can try and do it. But basically, these two proof are using first isomorphism theorem, correspondence theorems. Okay, so I don't want to do those proof. So first statement is about the Noetherian property is closed under taking quotient. Okay, so meaning if you start with a Noetherian ring and then you quotient it by an ideal, it's still Noetherian. Okay, I think this is not hard to imagine, right? It's not hard to imagine because taking quotient, you should imagine that you have less stuff, right? Okay, so suppose R is Noetherian. Okay, and I an ideal. Then R quotient I is still Noetherian. Okay, so this proof uses a first isomorphism theorem and a correspondence theorem. Second, this is very algebra geometry property here. So Noetherian property is also closed under localization. Okay, so I'll let you see what's localization. Localization is a very common operation you take in algebraic geometry. Okay, let's tell you what's localization here. So if you start with R, not just Noetherian ring, we want it to be integral domain also. Okay, Noetherian integral domain. And K is the its field of fraction. So in this section here, we will often look at the field of fraction of a ring because sometimes we want to divide by some elements inside to be convenient for our argument. Okay, so we'll consider field of fraction here. You know what's a field of fraction here? So you try and invert all the elements inside your ring. Okay, you invert them. So you add in the multiplicative inverse. For example, what's a pure fraction of Z? Q. Okay. All right. So what we do is we take a non-empty subset of R. Okay. And then we will define what is S inverse R. Okay, or sometimes you can see like this, like this. But I mean, real algebra person don't do this. They will write S inverse R. Okay, but I write this up to let you imagine what's the element inside there looks like. So if I already look right so clear, right, how does the element looks like here? A over B, okay, in the field of fraction such that A is in A, okay, and B either is 1 or a product of element in S. Okay, we can take product of element in S. Okay, so this is called localization. A in A. What is A? Huh? Why suddenly got A one? E lah. Okay, never mind. A in A. Oh, I know why it's 8A. Maybe that boot is A over I. So I forget to change it. I often make this kind of mistake, so please help me to multiplication. Okay. So we won't prove these two statements in class. They are just first isomorphism type of argument here. 我没有写完，哪里没有写完？
你应该说 R over S is also Noetherian.
Oh, right. Yes. Thank you. Then this is a Noetherian. And also, sometimes when I say proof by cases, right, I list three cases for you. And then I prove one cases, I'm very happy, then I leave already. So you need to remind me also. I try to remind myself. Now I try to check myself, but when I first started teaching, I often forget the other cases. Okay, so please remind me. Okay, so let's go to the next one. So we did do a very big, instead, without proving these two, we'll do a big theorem here. This is the Hilbert basis theorem. Okay, we're going to prove this. So this Hilbert basis theorem says that for any ring R, if R is Noetherian, it will implies that R adjoint X is Noetherian. Okay, actually, you might think that hey, this statement looks very simple. Okay, actually, it's very hard to prove. You adjoin one thing into it, still Noetherian, very hard to prove. Okay, so you will see a lot of proof in the market. Okay, a lot of proof. There's one very computational proof using Grobner basis. Yeah, Grobner basis. But I think I didn't do it in AA1, and so we won't use that method. Actually, Grobner basis quite useful if you try to go to computational algebraic geometry. Okay, it's very useful. Okay, but I don't think we will do Grobner basis in this class also. Okay, the first time I see Grobner basis is in commutative algebra reading course. Okay, so there's a special course just to read commutative algebra. Okay. All right. So the proof I'm going to present here is more sneaky proof here. So we'll do contra-positive proof. I have another proof which is a direct proof, but we won't do that. It's very long, but I will write it in the lecture notes. So what we're going to use is use a contra-positive. Okay, so meaning that we show that if R adjoint X is not Noetherian, if it is not Noetherian, then neither is R. Okay. Right. So which Noetherian property is useful here? So we're gonna let I be an ideal of Rx that is not finite generated. Okay. It's not finite generated. So what's the contradiction here? I'm going to show that R is not Noetherian. Okay, and the goal is we're going to produce a non-terminating ascending chain in R. Okay. We're going to produce a non-terminating ascending chain in R, thereby showing that R is not Noetherian. Okay, so this is our goal. So the goal is produce ascending chain. Okay, produce non-terminating ascending chain of ideal. Okay, so this is our goal. Right, so how to produce that? Huh? What? Okay. Well, so instead of picking a random one, right, we can pick a least one. So let F1 be a polynomial of least ideal, least degree, sorry, least degree. Ideal, and then we can choose keep picking. Okay, so we just pick fk plus 1. So let's say fk already chosen. So how to pick the next one? Okay, so let's tell you how to pick the next one if I pick the previous one already. So we will pick sk plus 1 to be the next least degree, right? Polynomial of least degree. So it will be a polynomial of the least degree. In the ideal, taking away the ideal generated by f1 up to fk. Okay. But you want to produce an ideal in R. Okay, so does this fi give you something in R or not? Does this fi give you something in R or not? This fi, how do you write this polynomial down? How does this polynomial looks like? Coefficient times the power of x, right? And then take a finite sum of them. Okay, so we will pick up the leading coefficient. Okay, so let nk be the degree, and ak will be the leading coefficient of fk. Okay, so we pick up the leading coefficient. So by the choice of fk, okay, we will see that actually this ni should be increasing. Okay, moreover, the ascending chain that we consider is just ideal generated by a1, ideal generated by a1, a2, and we continue adjoining the leading term from higher degree. And the claim is, so this is the claim here. So the claim is this is a chain of ideal that does not become stationary. Not very obvious actually. Not very obvious. What if the leading term is the same? Not very obvious, huh? Okay. So let's do a contradiction proof here. So let's suppose. Okay, just suppose. Actually, for sake of contradiction. For sake of contradiction. For sake of contradiction, let's suppose it stops somewhere. Yeah, let's say AK. The ideal generated by A1 up to AK is the ideal generated by A1, A1, AK plus 1. Okay. Okay, so here is the contradiction proof. So maybe you might think that the contradiction proof very trivial, at least for me. Sometimes not to say trivial, it's like a trick. Okay, often we will forget this trick, but very important that there's some fact follows from this trick. Okay, so sometimes if we forgot this trick, right, we will forget how the facts work. Okay, so what I want to say here is even though it's not direct proof, it's still very important. Okay. Okay, so then what can we write down here? We could write down an equation, okay, about AK plus 1. No, because these two ideals is the same. Okay, we can generate AK plus 1 from A1 up to AK. Very, very simple. Write down as a linear combination. Sorry? Sure, for some K, yeah. For some K. If this K works, then it will work for all K. Okay. And then we will define some guy called G. Okay, so what's this G here? G will be Fk plus 1 minus the sum of I from 1 to K on Bi. Okay, so let's see what I'm going to do here, and then I tell you what happens. And this Bi here, I want to multiply it with some X with a carefully crafted power here. So here is Nk plus 1 minus Ni. Okay. The claim here is this guy should live in I take away the ideal generated by F1, F2 up to Fk. Okay, let's look at this elements here first. Let's think about this element. What am I doing here? What am I doing here? What am I doing here? This AK plus 1 is a leading coefficient for Fn plus 1. Okay. And then what? We know that we can split this AK plus 1 into the sum of this product. Okay. So I think how about we write it out? Let's write it out here. How should we write it better? So Fk plus 1, we can pull out the leading term here. So the leading power should be Nk, right? Like this. Okay. And then plus blah, 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 or something else. Okay, which is a finite sum. And then we need to take away this bunch of thing here. Copy. Paste. Wait. Okay. 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 What happens? I hope I didn't copy wrong. Let's analyze. What's this? Anything wrong here? Let me see. This is what I want. I think the goal here is I want to take away the leading term. Can I take away leading term using this construction here? Can or not? Can this disappear? How? Huh? How? Which K give you that term? Huh? Oh, sorry. So here should be MK. Okay. Okay, and then where's the cancellation? Where's the cancellation here? So 可以讲英文吗？
If you pick every monomial in Fi that is have the highest degree, and if you times the bi things in front that thing and plus them, you will cancel it.
Guys, can you understand? You can. Wow. Okay. You repeat. I try repeat. Or use your understanding. Yes. 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 Everyone heard or not? You didn't hear? You do not still understand? You don't understand? Okay. So basically what we do was we write AK plus 1 as a linear combination of the leading term. Okay. So meaning what? This AI only appear in the leading term of each Fi. Okay. So what's the difference between AK plus 1 and the AI here? Then the difference is this guy. And one more different. The power of the X is different. So you need to so you need to change that. I don't want to say change that. I want to say you need to compensate. Okay, compensate the difference of X between the leading term of Fi and S to the NPM. Okay, you need to add up to NPM. So that they are in the same monomial, right? Only then the coefficient can pair up. Okay, does that make sense? Question? Question? Please ask. You have a question? Please ask. 来，嘉怡，有问题吗？ You cannot understand. Which part cannot understand? You know, sure. No. Like this. If you don't understand, right? 一定有一个解的，或者有10个解。你不要想一下子解决完了，不可能的事情。你要一个一个解打开，从最开始的地方打开。OK， OK 了。Okay, so we have to write it out. Do we write it out? Okay, let's write something down. Okay. Yeah. Hey, what happened? Okay. You what? Yeah, try again. Yeah, so I guess one thing in my class, right? 在我的班上你要练你的听力。我可能讲对的东西，我有可能讲错的东西。对跟错你都要听出来。Yes, in my class, you need to listen. You need to train your listening. Okay, because maybe some lecture I just read. They expect you to read yourself actually. Okay, so I will say something wrong and something right. Okay, both you need to catch. Does it make sense? Yeah, this is how you communicate with people. Okay. Because I saw a lot of people with a communication problem 天天跟人家吵架人，他就是听不懂人家讲什么，他根本没有在听你讲什么。Okay, yeah. Those who like to quarrel with people, fight with people, they didn't listen carefully what people say. Okay, so please listen. All right. So what I meant here was, if you try and split up, let's say. Okay, so let's write down. Let's write. Should I write it down? 感觉很恐怖如果把它写上。Anyways, let's write it down. Okay, so this is what I meant, right? Okay, but what is F1? How do we pick F1? F1 has a leading degree of n1. Where f1 have a leading degree of n1. With the leading term a1. Okay, so here we'll have snk plus 1 minus n1 times a1 x to the n1 plus something else. I don't know what is that thing. Something else. Finite sum. And so on. bk times x n k 1 minus sk of ak s n k. Okay. So notice that if you try and distribute this extra term here into your fi, you will upgrade your leading power to the same power as to the nk. And then if you look at the linear combination of these bi with ai, the sum of them is equal to ak plus 1. But we are taking the subtraction. So this okay. And for a okay. 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 So one thing I want to prove to you is whenever we are talking, right, we are talking something concrete. And so make sure that when you say, you know how to do it. Okay. And then the other thing you need to train is when you do it, you need to know how to say. Okay, so this is the two direction into learning class. Otherwise, if you go it's very hard. You cannot communicate. Okay. Are we done yet? Are we done? If we cancel this guy, right, what happens? This is a lower degree than fk plus 1. But remember how we choose fk plus 1? We are picking from this complement here. That is the smallest degree. But now you found a smaller one, even smaller. Okay, so you GG. Contradicting the minimality of fk plus 1. The choice of. So meaning what? Actually, the coefficient here is quite sensitive. The coefficient here is quite sensitive. Okay. Any question? Okay, if no question, let's continue. Let's continue. So now I'm gonna do PID now. So we finished the Noetherian part. So this is the as many Noetherian knowledge you need for later. Maybe there are more in tutorial question, but that's the basic one you need to know. Definition. Let's define PID. Remind you what is a PID. I think we did the PID in abstract algebra 1 at the back, quite behind, and we didn't do any assignment or test about it. Okay, so let's start with PID here. So what's the PID here? PID is an integral domain. It's an integral domain in which every ideal is principal. Yeah, that's why we call it a principal ideal domain. Okay, domain refer to the integral domain, and then principal ideal referring every ideal is principal. Okay, so that is what is principal ideal? I still remember or not? It is generated by one element. Okay, good. Okay, so basically they are all the multiples of that generators. Okay, for some. Okay, very good. Next thing is we want to define what's a irreducible mean. So an element A, non-zero element in a ring is said to be irreducible if A is not unique, and whenever you can split it up, then one of them must be a unit. For example, let's give some example here. So 7 is irreducible in Z. Okay, you might think that, oh, 7 is prime in Z, right? Okay, so we have another notion of prime actually. So we split out the notion of prime and irreducible. So an element, a non-zero element still in R is said to be prime if A is not a unit, and whenever A divide BC, then either A divide B or A divide C. Okay? So you might think that, right, this is also a property of a prime number. Sure, 7 is also prime itself. Okay, but I'm gonna show you that not every irreducible element is prime, and not every prime is irreducible. Okay, so let's give you some idea why this could happen. Okay, so they don't always imply each other. So let's start with not every irreducible element is prime. Okay, so proof. Let's consider this special element here, A plus I square root 5. Okay, this is living in the Gaussian integer of Z adjoint I square root 5. Okay, so we're going to show that this element here is irreducible but not prime. Okay, we're going to show that this element is irreducible but not prime. So irreducible means what? This is not a unit. Okay, and whenever A equals to BC, B or C has to be a unit. Okay. So, well, we should split it up first. Is it clear that this is not a unit? Can you find the multiplicative inverse of this guy? Well, let me ask you a question. Does 1 over 2 plus I square root 5 exist? 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 How? Like, tell me. Try. Want to try? Oh, you want to try or you want to try? Faiz or Hanping? Uh, 2 minus square root 5 over 9. How do you get this? Wait. How do you get this first? Conjugate, you mean? Conjugate. Okay, so you take the conjugate of your denominator. But does this live in Z adjoint I squared 5 or not? No, right? Okay. Yeah. Okay, so it's not a unit. So let's say let's think that we can split it out. Okay, split it out to two elements in Z adjoint I squared 5. So let's say I plus IB squared 5 and C times C plus ID squared 5. Okay, for some A, B, C, D. And let's say we can split it up. Okay. Product of two elements inside the Gaussian integer. And then what can we get here? Is it okay that I say that it is a length? So if we consider the length Euclidean norm. Oh, is it Euclidean? But here is a Gaussian integer. Do we call it Euclidean norm? Call it Euclidean norm? Norm. Okay, norm. So let's consider the norm. So we'll get that a squared plus 5b squared and c squared plus 5b squared. So, yeah, basically we multiply by the conjugate also. Okay. So there are few possibilities here. Okay, so in this case here, it's easy to handle because you just need to ask yourself what are the positive z that can multiply to 9. Right? It's positive, right? Sum of square. Okay. A square positive, 5 positive, b square positive. Okay. Sum of positive integer. So first case is either you get both of them to be equal to 3. Okay. This is the one way you can get 9. What are the other way you can get 9? 1 times 9, right? Or 9 times 1. Okay, so these two cases could happen. Actually, it doesn't matter, right? Depend on how we label A, B, C, D. But if we fix one A, B, C, D, then it matters. If we don't fix A, B, C, D, it doesn't matter actually. It's just a swap. Okay, I believe these are the only way you can get 9 from the product of two integers. Positive integer, positive. Okay. So, well, can 1 happen or not? Why? So you can you have to give me A and B that works. Okay, first case possible or not? Can the first case be possible? Why not? Why not? Why not? Why A and B can be 0 and 1? So if A and B, one of them is 2, should be too big. Okay, so 0 and 1, and then? Sure, you can just try all of them. Yeah, sure. You can just try all the 0 and 1. I just no. This is very true. Yeah, try all the 0 and 1. So it could be 0, 1, 1, 0, 0, 0, 1, 1. Yeah, also true. Yeah, also true. But the point here is try the 4 cases. Yeah. 5b squared is at least 5. If b is 1, if b is 0, then 5 doesn't matter. B could be 0. Yeah. So that's why you need to argue. Yeah. Okay. So, okay, so just try all the 0 and 1 cases. You'll see that the case 1 is impossible. Okay, so basically two main problem here. Since 3 is not a square, if you try all the cases, and then 5 is greater than 3 already. Okay? I think these are the two main problems if you try the cases. But case 2 and 3 could happen. If these two happen, that's fine, because the case 2 and 3 will imply that either a plus ib square root 5 is equals to plus minus 1, or c plus id square root 5 is equals to plus minus 1. Okay? Can follow? Okay. So in this case here, we have proven that 2 plus I square root 5 is an irreducible element, because plus minus 1 should be a unit. It's a unit in the Gaussian integer. Okay. Next, we're gonna prove that this is not a prime. Okay, not a prime means what? Not a prime means what? So if you want to show that an element A is a prime, we need to show that if A divides some products, A must divide one of them. All right. So we also use a convenient products here. So notice that A plus 2 plus I square root 5 times its conjugate is 9. Okay, but we can write 9 as a square of 3. Okay, but this will implies what? Actually, this implies that A plus I square root 5 must divide 3. Okay. So we should be able to write 3 as a multiple of 2 plus I squared 5. But this multiple live in where? Live in the Gaussian integer here. Okay, for some AB. So can you find this AB or not? Such that it works. So if you multiply it out, right, what do you get? You should get 3 equals to 2A minus 5B and then A plus 2B here. Okay. But if you try to solve this linear equation here, what do you get? Hang Wei, what do you get? If you try and solve this linear equation here, linear system. What do you get? Solving, okay. I need to take attendance. So let's take a picture. Okay. So what's the system of linear equation solved here? Wait. You hungry? I hungry. What do you get? I think you shouldn't spend more than 10 seconds here. I'm not laughing, It's just that I want to correct your way of thinking. What should you do here? What's the easiest substitution you can do here? I hungry. What's the easiest substitution you can do here? Listen to me, no need to see already. Listen to me. What's the easiest substitution you can see here from these two equations? What? Say again? What are you talking about? What is 2 and minus 1? Wait, I mean, so you don't know what it means by solving linear system. Okay. So what's the easiest substitution you can see here? Substitution. Something becomes the other thing. So A equals to what? A equals to what? Wait. A equal to what? You even finish it. Okay. So if you sub here, what do you get? 2 times your minus 2b, what you get? Good. Minus 4b plus minus 5b. Yes, this is what I meant by 10 seconds. Okay or not? Okay. So more importantly, 3 equals to minus 3b. Can this happen or not? Cannot. Okay, so what? 3 equals to minus 9b. Oh, I said something wrong. Huh? Okay, so 3 equals to minus 9b. Can it happen or not? Okay, so contradicting that. Is in Z. Okay, so 2 plus I square root 5 doesn't divide 3. Okay, and so 2 plus I square root 5 is not an prime element in Z, adjoint I square root 5. Okay. Okay, let's do one last one. I think we can finish there. So next part, we're going to show that not every prime element is irreducible. Okay, so meaning you want to show that it is not irreducible, right? So what's not irreducible means? You want to show that if you can split it up, neither one of them is a unique. Okay, so you need to start from this kind of idea. Okay, you should start from this kind of idea. Okay, so let's start from this idea here. So in Z6, okay, let's go to Z6 and find it. We actually want to show that X3, the coset 3 is a prime element but not irreducible. Okay. So in Z6, what are the unique here? How many uniques are here? There are only 2. Okay, these 2 are the number that are called prime to 3. Sorry, 6. Okay, so what are the number called prime to 6 in Z6? 1 and 5. Okay, 1 and 5. Okay. Okay, let me ask you, what is the inverse of 5 here? Multiplicative inverse. 5. Why? 5 times 5 is 5 times 5 is 30. Okay, 35. So 35 more 6 is 1. Okay, good, very good. Yeah. I accept your mistake because I also make mistake. Okay, since we can write 3 equals to 3 times 3. And 3 is not a unique. Then this is how we reduce it. Okay, so we say that 3 is reducible. Okay, then we're going to show that it is a prime element. Okay, so prime element means what? If 3 can divide some product, then 3 have to divide each term in the product. So now we will show that. I have 2 minutes. Let's finish in 2 minutes. So let's show that this 3 here is a prime element. Okay, I purposely put a bar here because later we want to move our argument back to Z. Okay, let's see how we do this. So obviously, 3 bar is not a unique. Okay, just now we already discussed already. And now suppose 3 divide product of 2 element. Then this means what? This means that this product is a multiple of 3. Okay, it's a multiple of 3. Okay, very straightforward. Now we're going to transfer this statement into Z. In particular, in Z6, meaning what? Their difference is a multiple of 6. Okay, so their difference is multiple of 6. Or the remainder is divisible by 6. If it is divisible by 6, obviously it is divisible by 3. Okay, by transitivity of divisibility. Since 3C is divisible by 3, right? If you want to divide this whole thing here, you need to have 3 divided by AB. Okay, but a good news is 3 is prime. And 3 is prime in Z. So 3 will divide A or 3 will divide B. So if you look at the equivalent class, we also have either 3 bar divide A bar or 3 bar divide B bar as designed. Okay? 550. Any question? Before we leave. Any question? Okay, we will continue this commutative algebra. Hopefully, we will spend 1 or 2 more hours. 1 or 2 more hours. Then we will move into affine varieties. Okay, yeah, the main character of this course, main dish. Okay, now it's entree. Still entree. Algebra entree. Okay, so see you next week. I'll try come up with assignment this week, and then we'll see how it goes.
Actually 你可以给我讲一个那个the converse of Algebraic basis theorem 怎么样？